Hey everybody, it's Tuesday, February 2nd, and as you can see here in the aim today, our goal for today's video is all about how we can use graphs to represent energy conservation in physical systems. Essentially what we're doing here is we're wrapping up conservation of energy. We will be done with conservation of energy by tomorrow. Essentially, we are actually already done with the new content, basically. This last little thing that I'm going to show you in this video here today is really the final piece of new information. Tomorrow, what we're going to do is we are basically going to do like a little summary activity. It's a video lab where we put everything we learned in conservation of energy to use to basically solve a problem. I don't want to give too much away about it here now. The basic point behind this last little piece of information in this unit is the redesign of the AP Physics course, which took place, I guess now 7 years ago, wanted to focus on making a physics course that didn't involve you in just taking numbers and jamming them into equations and getting them to spit out an answer. They really wanted you to represent your physics knowledge in a variety of different ways. And so that's why you'll notice there are a lot of explanations in these problems. They have you draw diagrams and really focus on those sort of pictorial representations of these things. Obviously, graphs are a big piece of this. And these kinds of graphs, which is not just like a standard y versus x-axis graph that we're going to look at here today, these kind of graphs are really one of these like new little trendy things that they're doing in physics education to try to sort of round out your understanding of physics and sort of get you to be able to explain and represent your understanding in a variety of different ways. It's probably appropriate to just start right off the bat and be fully transparent in telling you that I think these things are kind of stupid, frankly. I'll tell you that up front. But nevertheless, the people who developed these kinds of representation schemes for physics, the way that you can show conservation of energy in a variety of ways, a lot of these people were heavily involved in the redesign of the course. And so because they invented all these things and then were paid a bunch of money by the College Board to redesign the course, there is a reasonable amount of possibility that these kinds of things are going to appear on the test. And so I want to make sure that everybody is able to sort of at least see these a few times before you take the test, just so you're familiar with them should you ever have to deal with them. I also think it's probably important to say up front, I do think these things are remarkably simple. I think once you see me do one example of these, you will find it to be very straightforward. Having said that, it's important to just cover the whole thing, have everybody take a look at it, and then we'll do some practice. And then ultimately, like I mentioned, we'll put it to use in the video lab tomorrow. So again, the main point of what we're doing here, or what we want to say, is that despite the fact that you can solve a lot of complicated conservation of energy problems, the concepts are simple. Really, as it says here, to some degree, because conservation of energy problems are basically just accounting problems, we can represent the fact that energy in a system is conserved in a variety of ways. I'm pretty sure when you guys were in honors physics, I said this, and if you had Miss Near on, I'm pretty sure she used to say this as well. A reasonable way that you can think about conservation of energy is by thinking about money, or even like just money in a bank account. We always say, first off, that energy can exist in a variety of forms. Money can exist in a variety of forms. It could exist as dollars or quarters, nickels, dimes, whatever. It can also exist as checks. It can also exist digitally, like in a bank account when you don't actually have the physical manifestation of the money, right? And essentially like transactions that you can make with your money, whether you get paid and the amount of money in your bank account increases, or you pay somebody and the amount of money in your bank account decreases, sort of operates in a similar fashion to the way that we think about the energy possessed by an object. Here, the transactions, whether you get paid or pay somebody, functions as work. And the amount of money in the bank account going up or down really represents like the total energy in the system. It's kind of a kiddie way to think about it, but it serves as a relatively useful mental model. And so you can have the money existing in a variety of forms, being transferred between different forms or in different amounts. And so that's the idea. And one of the ways that we are going to represent the fact that basically these conservation of energy problems are just accounting problems is we are going to use these graphs. Sometimes we can actually refer to them as a chart because they don't really work like an y versus x axis plot. And so one of the ways we can do this is by making use of these things we can call energy bar charts. And that's really what we're going to spend the very beginning of this video talking about, and then we'll look at a couple of examples of how these could be used. Before we get into the specifics of what an energy bar chart is and how we can represent conservation of energy using these energy bar charts, I'd like you to take a second to pause this video here and write that down. And when you hit play, we'll get into the specific details about energy bar charts. So you can write all this under the heading energy bar charts. The first thing that we can say about energy bar charts here is energy bar charts are used to graphically represent the amount and type of energy present in the initial and final states of a system. And so depending on the exact situation, and you'll see what I'm talking about here when we take a look at our first example, they will show you a bunch of different kinds of energy sometimes, or just one kind of energy sometimes. And essentially what you'll have to do is you will have to draw in the values of these charts. It's basically just like a column graph to show the different amounts of energy existing in different forms. And of course, the heights of these charts, or the heights of these columns in the chart, represent the amount of energy. And if you see the amount staying the same, you know the energy is conserved. And if you see it being different, then you know there was some work done. That's really the point. Like I said, it's kind of kiddie, it's kind of childish, but it's something that you could expect to see. And so I want to make sure you are prepared for all of it. The second thing we can say here is that, like I mentioned, this demonstrates that energy can be converted from one form to another if you see different forms of energy, present in the picture. But it can also represent the fact that energy is conserved when you see the heights of those bars staying the same over time between the initial state and the final state. And the other thing we can say here is that these energy bar charts can also represent any gained or lost energy by accounting for the amount of work done. And all of this is laid out on the chart. You'll see this here when we go through an example, and we're going to get to one of those very quickly. There are a couple more things I want to tell you very specifically about these charts, but this is really most of it, at least from a conceptual angle. So take a second to pause this video here and write that down. And when you hit play, we'll go ahead and talk about a few specific details for these charts before we take a look at an example. Okay, so a couple of things you definitely want to know as we go through this. And you'll see I'm going to address each and every one of these in probably the first example that we do. The first thing we'll say here is while these graphs aren't done with exact values, they're done to scale. Most of the time, they're not going to tell you the amount of initial energy or the amount of final energy, but they'll be able to give you enough information so that you'll know roughly how they compare. You won't know that the initial energy is 100 and the final energy is 200, but you'll know that the final energy is supposed to be double, something like that. So they're done to scale. Essentially, what you want to do is you want to use the information given in the problem to set the initial amount of energy. I'm going to go through this when we go through the first example. In the absence of external work, that's a crucial step because that's also going to be the total final amount of energy. It just may be distributed differently among the different types of energy. Of course, you already know this, though, because you've seen conservation of energy problems, right? I mean, sometimes the object starts out with kinetic energy and it finishes with all, like elastic potential energy, or sometimes it's split between two different kinds. But if the energy is conserved, the total amount remains the same. And the last thing we'll say here is that the total amount of work done on the system, of course, is equal to the change in the system's total energy, and that this must be represented to scale as well. Oftentimes, this is the last thing you fill in, of course, depending on the information they give you in the problem. And so we'll go through specifically how to represent that scale depending on the problem. Take a second to pause this video here and write that down. And when you hit play, we'll go ahead and just take a look at our first example. Let's take a look at an example. If you looked at the post carefully today, when where you found this video, you should have noticed that there was a sheet attached to this post for today that said AP Physics Energy Bar Charts Problem Solving Worksheet. I'd like you to go ahead and open that worksheet. This is the first problem on that worksheet. It's in that Tipper's book. It's B4 BCT 15. It says Object Changing Velocity 1, Work in Kinetic Energy Bar Chart. And it says here a 2 kilogram object changes its velocity as a force acts on it for 5 seconds. It changes its velocity from 4 meters per second east to 6 meters per second east, as shown. And it says complete the work and kinetic energy bar chart for this process. The bar heights should be in correct proportion to one another. Notice that's basically exactly what we said. And then it says to explain your reasoning. We're not going to go too nuts about the explain your reasoning part. We'll actually just go ahead and show that down here as we're going along. So before we actually go through and do the reasoning through the problem, I just want to show you the bar chart. If you have the attachment opened, you should be able to see that, but this is what the actual chart looks like. And so notice here they have the initial system energy, the final system energy, and then the external work, or the work that's done by external forces. And they have little tick marks here. Notice totally unlabeled except for the 0. So this is what I meant by you set the initial amount of energy and you set the final amount of energy. It's all up to you. And so basically what I want to do for this first one is I just want to lead you through the way that I approach these problems. I think you guys are smart enough to figure out whether you want to do it the way that I am showing or want to do it your own way. And then we'll go ahead and just take a look at a bunch of different examples. Okay, so the first thing that I'm noticing when I see this situation is the energy in this system is not conserved. How do I know that? Well, first of all, it says a force acts on the object for 5 seconds. And so that lets me know that there's probably some external work done, because the only thing they're talking about in this problem is the ball. And clearly I can see from the values given in the problem, the speed of the ball is increasing. And if the speed of the ball is increasing, that's telling me the kinetic energy is increasing. The obvious question here is, well, how much is the kinetic energy increasing by? And the answer is, I don't know. Because they told, well, in this particular case, we can figure it out, but a lot of times they don't. And so that's why I kind of told you I don't know here. A lot of times, I actually thought it was pretty funny that they gave you here that the mass of the object was 2 kilograms, because a lot of times I like to make up the mass of the object if you have to, and I make it up as 2 kilograms. The reason why is because I am very liable, because I sometimes am careless with my work, to make silly mistakes. And the fact that the kinetic energy equation is 1/2 mv squared means that whenever I do the 1/2 m, if my m is 2 kilograms, I know 1/2 of m is 1. And then I don't need to think that hard about what the kinetic energy is. In some cases, you will have to do that, and you will see this here later in this video. If you have to make up a mass, sometimes it's smart to just make it up as 2. Obviously, you can make it up as 1 also. You all know how to do math, so who cares? You just set it up as something that it's going to be easy to use. So because they told us the mass of this object here, we can actually just calculate the initial and final kinetic energies, and then this ends up being a piece of cake. The first thing we can say here, though, for the explain your reasoning part is the object exerting the force does work, which increases the object's kinetic energy. Okay, so now we could just go through with the initial and final energy calculation. Now, because this is not an official thing, you don't really need to go nuts about the knowns and unknowns. It's obviously all written right here. And the point of this is to make the graph. So we're going to do these calculations fairly quickly. So the initial kinetic energy here is going to be 1/2 mv naught squared. And we're going to write here 1/2 of the mass, which they told us was 2 kilograms. And then we're going to multiply that by the initial speed squared. And that's 4 meters per second. We square the whole thing. Now, of course, this ends up being easy because 1/2 of 2 is 1. And so essentially the energy here is just 4 squared, or 16 joules. Of course, the calculation for the final kinetic energy is just as straightforward here, because we have now the final kinetic energy is 1/2 mv final squared. And so that gives us 1/2 of that 2 kilogram mass. 1/2 of 2 is 1. And then we're going to multiply that by 6 meters per second, whole thing squared. And of course, 1/2 of 2 is 1. And so the answer here is just 6 squared, or 36 joules. And so basically, here's the part where you just need to think. Notice, none of this is labeled. So the obvious question here is, what am I supposed to do? And you're just supposed to look at the numbers. What number would it be smart to make those little incremental divisions on this chart? Would it be smart to make them 1 joule? No, because we're going to run out of room. There's not 36 bars here, so we can't do that. Would it be smart to make them 2? Yeah, it could be, but again, there's not enough room here. Would it be smart to make them 3? No, because they're both not divisible by 3. The smartest number to make these increments, in my view, at least to just start us out, is 4. And that's because 16 is divisible by 4. And so that means our initial energy is just going to be 1, 2, 3, 4 units. And so we'll go ahead and just color this in here and make our bar. And we can go ahead and color that in after the fact. I'm just going to sketch the bar here for now. And then that means because the final energy is 36, the final bar is going to be 9 units tall. 1, 2, 3, 4, 5, 6, 7, 8, 9. And what do you know? That happens to be the maximum number of bars on the chart. And so they were kind of setting us up here for an easy one. And so, of course, once you get the bars sketched, it's a lot easier to do if you have like a pencil rather than on this computer drawing thing. But you could just like sort of sketch it in, color it in, make your bar nice and dark and whatever. So there's our final bar. Here's our initial bar. Bada boom, bada bing. And so now all we have to do is fill in that middle section of the graph. And as we mentioned here, this is not rocket science, right? This object ends up with 36 joules of energy. It started with 16 joules of energy. The question is, how much energy did it gain? Because work is equal to the change in energy. And clearly here, since the energy is increasing, we could rephrase that by saying work is equal to the gain in energy. And the energy gains here by 20 joules. No surprise. Now, of course, you could think about it like that and say, well, if each increment is 4 joules, then that means I've got to go 5 bars of height for my external work. So I'm going to go 1, 2, 3, 4, 5. But of course, now that we've already come up with this scale, we can just say the initial height of this first column here is 4. The second one is 9. And obviously 4 plus 5 is 9. And so that's why this one's got to be 5 units tall. And that's really it. That's an energy bar chart. It really is as simple as that. Of course, we've already taken a look at problems this year so far where we've said like an object has its speed increased from 4 to 6 and calculate the work done. The work is equal to the change in kinetic energy, and you had to go through and calculate it. This is just another sort of kiddie way to represent exactly how this works. And of course, you don't have to, but you could say that this initial system energy is 16 joules. We have 20 joules of work, and then we end up with 36 joules of final system kinetic energy. That is an energy bar chart. Like I mentioned, I think this is kind of silly. I am much more interested as a physics teacher in being able to tell you an object with a mass of 2 kilograms sped up from 4 to 6 meters per second. What is the amount of work done? What is the size of the force if it acted over this displacement? You guys have done that before already this year. This is just kind of another way to show that you know that, but really is actually much simpler, right? So if they give you any of these bar charts, this is the way you do it. Of course, there are some interesting concepts which can be revealed in some of these energy bar chart problems. And so I'd like you to take a look at this next example. And the question we want to ask here is just, what is the difference between this problem that we just did, B4 BCT 15, and this problem, which we're going to take a look at now, B4 BCT 16? This problem here says a 2 kilogram object changes its velocity as a force acts on it for 5 seconds. It changes its velocity from 4 meters per second east to 6 meters per second west as shown. Complete the work and complete the work and kinetic energy bar chart for this process. The bar heights should be in correct proportion to one another. The question here again is, how is this situation different from the last situation? I'd like you to take a minute to pause this video here and think about this. Think about what's happening with this force. Think about how it affects the object. Think about how it might affect the calculations. And then ultimately what I'd like you to do is think about how it would affect the chart. And when you hit play, we'll go over it. Whether it seems like it or not, the way that this changes the chart and the whole way we think about the problem is rather straightforward. It should be obvious to everybody that this object initially is moving east and thus has a positive initial velocity, and it's now moving west, and so it has a negative final velocity. And that is obviously a totally fundamentally different situation than the situation we encountered in the first example. And so the chart here that you would do for this particular example is actually just going to look exactly the same. That's the answer. Now, of course, the question is why? How is it possible that the chart is going to look the same, even though clearly what happened to the ball is different? It changed directions. The point is, energy is a scalar. And because energy is a scalar, the fact that the ball changed directions doesn't actually matter as far as calculating the initial energy, the final energy, and the amount of work done. This is an important concept, not just for these like silly little bar chart questions, but also for the AP test in general. Because the next topic that we are going to talk about, conservation of momentum, is a topic where we will often integrate momentum and energy ideas. And they will often, on AP questions, try to sucker you into thinking that the fact that the object changed direction means the energy analysis is fundamentally different, and it's not. Energy is a scalar. Even if you think about the equation 1/2 mv squared, if you plug in 1/2 of 2 kilograms times positive 6 meters per second, you get 36 joules. And if you plug in 1/2 of 2 kilograms times negative 6 meters per second, you still get positive 36 joules because the negative number squared is positive. Now, you shouldn't even be plugging in -6, of course, because kinetic energy is a scalar. The V definitely stands for speed and not velocity, but that's the idea. Now, of course, we should probably be thinking that there are some pretty reasonable questions we could ask, because clearly what's happening is different. That force, if it was going to act for the same amount of time, must have been acting in a different way, either over a greater displacement or with a larger magnitude. If instead of just speeding the object up from 4 to 6, if it made the object go from 4 meters per second all the way down to 0, and then sped the object up from 0 to 6 in the opposite direction. And that, I think, is the point. The point here is that the work that's done when the ball is slowed down, when that force acts on this object opposite the direction of its displacement to make the final velocity 0, that work is negative. And that's a fact. But at some point in this 5 seconds, you end up having an object with a speed of 0 that has a force acting on it. And that force ends up speeding up the object. And so then positive work starts to be done on the object. And eventually, that force is going to speed the object up to a speed of 4 meters per second. And that work that's going to be done is positive. And it should be clear to everybody, based on the fact that work is equal to the change in kinetic energy, the negative amount of work that would be done in making an object go from 4 meters per second to 0 meters per second is the exact same amount of work, just positive now, to make an object go from 0 meters per second to 4 meters per second. So up to that point, the total amount of work done is 0, because there is negative work at some point in that problem, because obviously the object has slowed down from 4 meters per second to 0 in the midst of turning around. But that force continues to act on the object to increase its speed from 4 to 6, and that ultimately takes 20 joules of work. And that's why the total amount of work done here is the same. Work, whether it's positive or negative, only refers to whether it is increasing or decreasing the energy of the object. And in the beginning, when that work was done, it was decreasing the energy of the object. So that work definitely was negative. But then eventually, once it basically got rid of all of the object's energy and that force continued to act, the work that was done by that force was positive as it was increasing the energy of the object. Eventually, it canceled out all of the negative work, so there was no net work done up to the point where it made the velocity 4 meters per second. And then the only net amount of work was done in making the object go from 4 to 6, which was the exact situation that we had before. Net work done in order to make an object's speed, remember speed because energy is a scalar, its speed go from 4 to 6. Now, that was a lot of talking about that second example, and it would probably be smart to write at least a couple of things down about that specifically for this instance, that energy is a scalar, and so the direction of the velocities don't matter. So take a second to pause this video here and sort of summarize what we just said. And when you hit play, we'll go over it. Okay. So I'd like you to wrap up this discussion of energy bar charts by taking a quick look at the last two problems on this sheet. The last two problems on this sheet are two separate parts of BCT 17. In the beginning, the velocity of this tugboat changes from 2 meters per second west to 4 meters per second west, while a force is applied to the tugboat for 20 seconds. And then eventually, as it says in part B, the velocity of the tugboat changes from 4 meters per second west to 2 meters per second west, while a force is applied to the tugboat for 20 seconds. So take a couple minutes to pause this video here, answer these two questions. You don't need to write too much in the explain your reasoning thing. You just really need to talk about the work and what the work does to the object's energy. And when you think you've gotten both energy bar charts filled out correctly, I'd like you to hit play and we'll go over it. Okay, so let's start with part A. Part A says the velocity of a tugboat changes from 2 meters per second west to 4 meters per second west, while a force is applied to the tugboat for 20 seconds. And so the first thing that we're going to want to do here is recognize that this object, diagram is a little misleading, is going 2 meters per second first, and it's just going to the left or west, and then it's going 4 meters per second. So this happens first on the left, and then this happens second. And so the object is clearly speeding up. It was going 2 meters per second, now it's going 4 meters per second. So this object is going to be gaining energy. And to figure out the amount of energy here, we're just going to use the equation 1/2 m v initial squared. And of course, in this particular problem, they didn't tell us the amount of mass. Now, every single year, everybody differs. Some kids like to use what I just said before and say, let's say the mass is 2 kilograms, and we'll just do that. Some kids like to solve it in terms of m and do it that way. However you want to do it is entirely up to you. Because I would imagine a decent amount of you who are paying attention to what I was saying in the beginning just decided to call the mass 2 kilograms, and that's fine. I'm actually going to go ahead and call the mass 1 kilogram to make an important point, which is that our charts don't all have to look the same, and our charts don't all have to assume the same values, just as long as the proportions are correct. And so if your proportions are the same as my proportions, then it doesn't really matter. And so we'll say here, to start us off, we'll say the initial kinetic energy, assuming the mass here is 1 kilogram, is 1/2 of 1 kilogram times 2 meters per second squared. So of course now my 1/2 m is just going to be a half. I put that square on the inside, it should be on the outside there. 2 squared is 4, times a half is going to give me an energy of 2 joules. For my final kinetic energy, same thing, I have 1/2 mv final squared, so that's 1/2 of 1 kilogram times 4 meters per second squared. 4 squared is 16, half of that is 8. And so notice here, my energy is gone, from 2 to 8. So the force does work to increase the energy. And so now we can represent that information in our chart in a very simple way. If you remember from before, in particular, that these charts have 9 lines, the fact that we assumed a mass so small, which is actually an advantage of choosing 1 kilogram, the fact that we assumed a mass so small that our energies are just 2 joules and 8 joules means we can just make this first one 2 lines, make the second one 8 lines. Notice I said there were 9 lines, so we just need to go 1 below the top. And there's our 8 joules. We don't have to go nuts about making sure we're counting the individual lines right. And that's it. That's my initial and final kinetic energies plotted on the energy bar chart. So notice here, if you didn't have the exact same heights as me, that's fine. The only difference, of course, is that your final energy should be shown as being 4 times higher than your initial energy. So if you made this one 4 tick marks high and this one 1 tick mark high, that's fine. Now, of course, we need to fill in the external work with the difference. And of course, if we started off with 2 joules and we ended up with 8 joules, then the difference is going to be 6 joules. And so that's 2 joules lower. And that's it. Like I said, kind of kiddie, kind of childish. But should they ever ask these of you on the AP test, you want to at least be vaguely familiar with them. And so that's it for A. Moving on to B, we can say here for B now, it says the velocity of the tugboat now changes from 4 meters per second, which it just was at the end of that interval that we considered. Now it goes back down to 2 meters per second west after that force is applied for 20 seconds. And so it should be noted here that we know the amount of energy associated with 4 meters per second for this boat. Using my numbers, at least, it was 8 joules. And we know the amount of energy associated with this speed. Using my numbers, at least, it was 2 joules. It doesn't really matter what you chose, again, just so long as this one is 4 times the amount of that one. And so to make our chart here, our initial energy now is just going to be 8 joules, and our final energy is going to be 2 joules. So of course the question is, what's the difference? Now, this force is acting opposite the direction of the object's motion. And so we can say here that the work done by the force decreases the object's energy. And so that's really it. If the work done by the force decreases the object's kinetic energy, that means the only difference between the work done here and the work done in the last example is that the work is negative. And we'll make it 6 bars high. And that's really it. Notice if we add the initial energy to the work, we should always get the final energy. That reflects essentially this conservation of energy idea or the work energy theorem. And so we take 8 plus negative 6 and we get 2. And that's really it. Just so long as the proportions are correct and whatever this value is plus this value is equal to this value, then you're good. And that's really it for energy bar charts. And as you can see, the energy bar charts contain a lot of good information, but they don't contain every single thing you can know about a system. And so some genius physics teachers across the country decided there must be some way that we can make energy bar charts contain more information and be so cool and fun for children all across the land. And they decided to come up with their invention they call LOL diagrams. Yes, that is serious. They call them LOL diagrams because they want you to think it's fun because it says LOL, because they look like this. And really all I want to do in the remainder of this video is just tell you what these are, how they work, and how you can use them, because we're going to use them in the video lab for tomorrow. The idea behind these diagrams, at least, is that they're a little more useful to some degree because they really can help you write the conservation of energy equation. Now, you guys already know how to do that, so I'm not really worried about that. But essentially what they do is they show the amount of energy on these axes. I'm going to write this down in a second. They show the different types of energy here, and they do the same thing on this side. And then here is where they write the parts of the system, all the objects that are contained in the system. And the way they represent work being done on or by the system is they have arrows showing whether the work is negative, and so it's taking energy away from the system, and so they have the arrow going out, or they have the work being shown as positive, and they have the arrow coming in. Of course, you can use this to write the conservation of energy equation if you want. And so really what we're going to say about these diagrams are three things. The first thing we're going to say is the axes for the graphs on the left and right are used to keep track of the amount of initial and final energies and what type of energies are present in the system. The circle in the middle, as we mentioned, is used to identify the objects in the system. Arrows going into or out of the system are used to show any energy that is added to or taken away from the system. And that's really it. I'd like you to take a minute to pause this video here and make a basic sketch of what we drew, on this slide, and write down these 3 notes. And that will set us up perfectly for our video lab tomorrow. And so tomorrow, the first thing we're going to do at the very beginning of this video, after I give a sort of overview of the experiment that we're going to be doing tomorrow, is we are going to start with the worksheet, which we're going to use to compile our data for this experiment. Is we're going to fill out these kinds of charts for this particular system. I'll just show you the system now, so maybe you can start to toss some ideas around in your head for exactly how this lab might go. So first we're going to fill out these charts. Notice it says here initial to full compression of the spring and initial to highest point on return trip. This is the setup for the video lab tomorrow. We're going to have a cart rolling down a ramp and crashing into a spring. The video is 1 second. It looks like that. And so basically what we're going to do is we're going to draw that first diagram from here to here, where it fully compresses the spring. And then we're going to do it again for the whole thing. And what you'll notice we'll be able to do, as it says here at the bottom, is we're going to be able to calculate the spring constant for the spring, and we'll be able to calculate the work that's done by friction by collecting the data that's shown here. And then we'll be able to do some nice analysis questions here at the end. But with that, that's it for today. Have a good one, everybody.